And he's so it's the bears. Why would you start from That's true. The number 4 one? Yeah.
All right. Let me go over the calendar. This is the bottom of the page here. This is going to be a pretty short unit. We're just going to have a quiz over this unit. Mainly it's just related rates. But we're going to tack on two small topics, linear approximation and L'Hopital's rule. We're going to revisit limits from a derivative perspective. So, but that should be pretty quick, pretty easy. This related rates, that takes a little bit longer. So we'll do linear approximation today. And then if we have time, we can start related rates. Tomorrow and Wednesday will be related rates days. Thursday, we'll do L'Hopital's rule, but this won't take the whole period. So we'll definitely spend more time doing related rates. Friday, related rates, review, Monday review, and then quiz will be next Tuesday. Right. So we're just going to have a quiz over this units, and after this, we'll move on to the next units. Okay, so no test over on this unit. Okay. Okay, so page 1. It says the tangent line of a function f of x at x equals a can give you an approximate value of the function at that point close to a. So let me draw a graph here. Let's say we have this is the f of x graph. And then let's say we had a tangent line to this curve, and let me call that y of x. And let's say our tangent line was over here at 6. Let me just give us a random value here, 6 here. So here's my tangent line. My tangent line is going to share the same order pair and the slope as the curve at that point, x equals 6. Same point, same slope. Okay, that's the only point that the line is going to touch the curve. Now, let's say we wanted to use the line to approximate a point on the curve. Let's say we wanted to approximate 6.1. So f of 6.1 would be over here. Okay. But then y of 6.1 maybe over here. Okay, will they be the same value? Will the curve at 6.1 be the same y value as the line at 6.1? They're not. Okay, but it should be pretty close, right? Because we're close to the point of tangency. So, we know that they meet exactly at 6. So if it's 6.1, 6.2, or 5.8, 5.7, we know that it won't be the same value, but it should be pretty close to each other. Now, what if I use like f of 10 versus y of 10? Will they be close to each other? Probably not, right? So that's the big idea is that, okay, if we're close to the point of tangency, our approximation should be decent. But if we're far away from our point of tangency, then all bets are off. We don't, there could be completely not even the same ballpark. So we don't have to worry about how accurate our approximation is. We just have to be able to know how to use a linear equation to approximate a value on the curve. Another thing to talk about is the shape of the curve is going to tell us whether our approximation is going to be higher or lower than the actual value. So we call a curve concave up if it kind of has this U shape that is pointing up. So anything that resembles a U, a parabola opening up is concave up. Anything that resembles a parabola opening down is concave down. So no matter where I draw a tangent line, is my tangent line going to sit above or below the curve? What do you guys think? Below, yeah. So the idea is that a tangent line, assuming it's concave up, is always going to underestimate the function value. Tangent line underestimates the function value. So that means y of 6.1 is going to be lower than f of 6.1. Right? Y of 5.8 is going to be lower than f of 5.8 because of the way that the shape of the graph is curved. We can kind of estimate, we can kind of figure out what's going on if I had a concave down graph, right? So imagine I had a tangent line to a concave down graph. Now, where does my line sit? Above or below the curve? Above. So therefore, any approximation that I use with my tangent line to approximate a point on the curve is always going to do what? Overestimate, yeah. So we don't have to worry about, okay, how much does it overestimate by? How much does it underestimate by? The big picture here is we know if we know the shape of the curve, then a tangent line is either going to underestimate or overestimate, and that's all we need to be able to say. We have to be able to find the approximations using the linear equation, and then to be able to say, okay, the graph is tangent to a concave up graph, therefore this approximation is underestimating. Or since my linear graph is tangent to a concave down graph, therefore my tangent line approximation is overestimating. Okay. Are we good with that? Okay. So the rest of this is just finding estimations using tangent line. Okay. So number one, we have our function that is concave up on the domain. So now we're dealing with a separate function. It's not these two graphs anymore. But we do have some information that is going to help us. We know the graph is concave up. So we know our graph is going to have a U shape that's opening up. And we have order pair and slope. Okay. Now, anytime we want to do, we call this a local linear approximation. Basically, we want to find an approximation using a linear graph that is close to the point of tangency. So it's local, it's close to the point of tangency. The first thing we do is we want to build that tangent line. Okay, so we should know how to do this, right? If I ask you to build a tangent line, what information do we need? Slope and what else do we need? A point, yeah. Do we have a point and a slope to work with? Or do the problem give us a point and a slope to work with? Yes, okay. So the point is 4, 5. The slope is 3. That's all we need, right? That's all we need to build our tangent line equation. Okay. So before we can answer part A, we first have to build our tangent line equation. So we'll do y minus y sub 1 is equal to m times x minus x sub 1. So here's my x1, y1. There's my slope m. So I can say y minus 5 is equal to my slope, which is 3 times x minus 4. And so this is the first piece that I need. Okay, we already know how to do this, right? This is nothing new. We've been working on this ever since the derivative quiz. So now the only thing left to do is to figure out how can we involve this decimal into my approximation. So where do you think this 3.8 is going to go in my linear graph? 3.8 goes in for what? For the x, yeah. And that's all there is to it. This whole section is we already know how to do this. Okay, you build your tangent line equation, and then whatever decimal they give you, just insert into the x. And whatever you get in results, that's your approximation of some curve using this tangent line. I'm going to just rearrange this so I can just get that y by itself. So I'm going to say y is equal to 3 times x minus 4 plus 5. So now I'm going to plug 3.8 in for x. I'm going to say y parentheses 3.8. That just indicates I'm about to insert 3.8 into my linear equation. And this is a calculator. Yeah, we can use our calculator. I'm not going to ask you to do a bunch of number crunching with decimals. And this unit, you'll get to use your calculator. This ends up giving us 4.4. So this is what we can say. We can say that f of 3.8, which is the exact value on the curve at 3.8, can be approximated by y of 3.8, because we know y of 3.8 is going to be off of tangent, right? We know it's going to share the same point at order pair 4, 5, but anything that is close to 4, that's not exactly at 4, we know that the tangent line is no longer sitting on the curve, right? It's skimmed the surface, and now there's a gap between the actual value and the point on the curve. So y 3.8 is equal to 4.4. So this indicates that we're using a tangent line, to approximate the actual point on the curve, and our approximation is 4.4. And also, what can we say about 4.4? Is 4.4 going to be higher or lower than the actual value on the curve? We know it's concave up, so 4.4 is going to be where? Well, the 4.4 is sitting on the line. So is that 4.4 going to be below or above the actual value? Below, yeah. So we can say, since f of x is concave up, our linear approximation will produce an under approximation. Again, we don't have to worry about, okay, how accurate is my 4.4? We just know that it's some approximation, and we just know that the actual value is maybe higher than 4.4. Maybe it's 4.6, maybe it's 4.8. So when it comes to approximation, linear approximation, this is all College Board expects us to know. Can we find the approximation, and can we state whether it's higher or lower than the actual value? Okay, next up. Number 2, the function 5x minus 2x cubed minus 2 is concave down at x equals 1. So we know how the graph is shaped. Find the tangent line at x equals 1. So again, what information do we need? We need to find the what? Find the point and the slope, okay? Now this one doesn't quite give us the data that we need exactly. We have to go find it ourselves. How do I find the order pair? Plug 1 into the original function, okay? And then how can I find the slope? Yeah, 1 is the derivative. Good, okay, so try that. See if you can, basically, same problem as number 1. We just need a bit more work to get to the data that we need. We actually have to plug in and actually find it ourselves instead of them just giving us the value. Okay, power rule. We have our order pair, we have our slope, point slope form. Everybody okay? Building that tangent line. Okay. So now it says, what is the estimate of f of 1.1? So all we do is insert that decimal into our tangent line. So I just want to solve for y, plug in the 1.1, I get a value of 0.9. That's the approximation. We know that this is not going to be the exact value on the curve, whatever that curve value is. We could plug in 1.1 into the function, but you're never going to have to compare, okay, this is how far off we are from the actual value. We just have to be able to, it says local linear approximation, so we're using the line to approximate the point on the curve. So now part C, is this going to be overestimation or underestimation compared to the actual value on the curve? Over because why? Concave down, right? So any, we can just convince ourselves by drawing the graph, right? No matter where my tangent line is, if as long as my graph is shaped like this, like a U upside down, then my line is always going to skim the top of the curve. And I know that any point that lies on this line is going to be above the actual point on the curve. Overestimation. Okay, with number 2. Okay, here's number 3. Consider the differential equation dy dx equals e to the y times 2x squared minus 5x. Now, this sounds complicated, differential equation, but differential equation is just a fancy way of saying it's a derivative equation. It's just some derivative equation where if you give it enough information, in return, it'll give you a number, and that number is going to be the slope. So it's just kind of like f prime. It's just that it may look a little bit more complicated because it has y's and x's in it. But we learned from the last unit with implicit, right, that as long as we give it enough information, we can still find the slope just like any other derivative equation. So it says let y equals f of x be the particular solution to the differential equation with initial condition to 0. So there's my order pair. Write an equation for the line tangent to the curve at the point 2, 0. So I have my order pair. I want to create my tangent line equation. What else do I need? Slope. Okay, so define a slope. How can we do that? We have something to help us find the slope. We have the what? Do we have a slope formula? Yes, right. The differential equation, that dy dx is my y prime, is my f prime. So use this order pair, insert into your derivative equation, get your slope, exact same as parts above, right? You gather enough information, create your tangent line equation, and then we can worry about the decimal for part B. Okay, try that. See if you can find your slope and do point slope just like above. Okay, so plug in 2 in for x, 0 in for y. Anything raised to the 0 power is going to be 1. So 1 times, and then this is 8 minus 10, which is -2. -2 times 1 is -2. So there's my order pair, my slope I just found, and here's my point slope form.
It's not x plus. What's in the parentheses? Is it because the.
Well, the slope is -2, but it's going to be y minus y sub 1 equals.
It's positive.
Oh, you mean this 2 right here?
Yeah.
So let's see, y minus y sub 1, so it's going to be y minus 0 equals m, which is -2, times x minus x sub 1, so x minus 2, yeah. Okay, so good with part A. Next part, use the tangent line to approximate 2.2, so we can just plug 2.2 into the x, and that's our approximated y value using this linear graph. Okay, we're doing just more of these practices where you're just building your tangent line equation and plugging in the decimal. So okay, let's try number 1. This should feel pretty easy. This should feel similar to number 1, since you don't even have to get the order pair and slope. They give you that information. So use the given information and linear approximation to approximate the value of the function at x equals c. So find the tangent line equation. So that's the first step. Then plug in the decimal. So I know linear approximation, that combination of words sounds complicated, but really you're just building the tangent line. That's the linear portion, and then the approximation is where the decimal gets inserted. And really that's all there is to it. Okay. All right, try that. So you have your order pair, you have your slope, build your tangent line, and then you can plug in your decimal value. You can use your calculator if you have one. All right, are we okay with number 1? Okay, 2, 3, and 4 should go pretty quick. Go ahead and try those, and then we can work on page 3. Okay, check your answers for 3 and 4. Any questions there? Okay, let's go to page 3. Okay, so here's page 3. Use linear approximation to approximate f of 1.02. Now, we're going to have to build a tangent line first and then plug in the decimal. So guess what x value we want to use to build our tangent line? What's a nearby value that will be an easy value for us to start with? 1, yeah. So this is going to be the center of our equation. We want to use a nice, easy number close to our approximation value, but we want to build everything off of 1, and then we can do decimal at 1.02. Same thing here. We want to choose 1 here, and then for 7, we want to build our tangent line at where x equals 2. Yeah. So we always want to build our tangent line at a nice number close to our decimal value. So same as before, we want to build your tangent line. We need order pair and slope. So find your order pair at 1, find your slope through your derivative at 1, build your tangent line, and then you can plug that 1.02 into your tangent line equation. Any questions with 5? So number 6, same idea. We want to find order pair. We want to find the slope. Order pair from the function, slope from the derivative. But in this case, what process do we have to use to find the derivative? Closure rule, yeah. So f prime g minus f g prime all over g squared. Build your derivative, plug in your closest integer value. So my order pair for number 6 is 1 comma 1/2. And then to slope, after I found my derivative, plug 1 in, I got 13/4. So there's my tangent line equation. And once I get my tangent line equation solved for y, then I can plug that decimal into the x, and whatever I get is my decimal approximation. All right, take a look at number 7. We want to find order pair and slope from the derivative first before we do anything with that 2.1. What do we have to find? What do we use? What x value do we want to use? 2, okay. So 2 into the function to get the y value, 2 into the derivative to get our slope. To get to the derivative, we'll use what rule? Main rule, yeah. Try that. So set up your parentheses with an outside exponent, outside derivative times inside derivative, build your derivative, plug in 2, clean that value down to a slope value, point slope form, and then finally the decimal gets inserted into the x. Okay, any questions? So your homework, we finished it in class. So tomorrow I'm just going to be checking pages 2 and 3. You've already completed it. We'll start related rates tomorrow. Today we're on a C schedule. We're having to do PSAT readiness check during homeroom. So you go to second period, but then after second period, we're going to go to homeroom. Homeroom will be from 10:15 to 10:45. Okay, all right, come get your phones.
You would think that's it. You would think that's pretty.
Talking about like the actual.
Yeah, like a. I was, I mean, I don't know what. Yeah. It's all.